All right, so again, these are the two supernovae that are extremely important to us, but for different reasons. For this one, of course, is because we have this historical record, and we can now measure the Crab Nebula, and the other one, of course, is the one that happened very recently, in human history in 1987. It occurred in the southern hemisphere. I think I already said that, but it was in what's called the Large Cloud of Magellan, which is a small satellite galaxy to the Milky Way. It's a little irregular galaxy that orbits the Milky Way. Anyhow, that's where this supernova occurred, and we still we're still looking at the remnants, and we even received neutrinos from that supernova and recorded those neutrinos. All right, so let's move on to the next thing. So that's, of course, these stellar corpses that we were talking about. So after the supernova, so remember, this supernovas only occur for massive stars. So you're going to have either a neutron star or a black hole. All right, and like I said before, there's a chapter all about the death of stars. So we'll get into what the conditions are for a star to become for one of these dead stars to become a neutron star or to become a black hole. It's mass. All right. If we just kind of step back just a moment and think about the history of how, what we thought about stars. Of course, it says Aristotle was the first one to kind of think about that stars give off heat, but he never thought about the fact that stars can evolve. Of course, that didn't come. Those ideas didn't come for a long, long time. There was another guy. He wasn't really a scientist. He was more of a philosopher, Immanuel Kant, and he thought about the stars and the fact that there's gravitation. He didn't really formulate a theory or anything like that. In the 1850s and the 1860s, Kelvin and Helmholtz, who were two scientists, actually worked out the mathematics, or tried to work out the mathematics of pressure and temperature to figure out what was going on with stars. Of course, they failed, but the reason they failed is because we didn't understand the atom back in 1860. It wasn't until the early part of the 20th century, the early 1900s, that we began to understand the atom with the invention of, or the discovery of what's called quantum mechanics. Excuse me. So Sir Arthur Eddington, who was a very famous astronomer who worked on several things. Actually, one of the things he proved was Einstein's theory of general relativity, but he also recognized the importance of mass as the source of energy. In the 1940s, of course, we started to have computers, very primitive computers to today's standards, certainly, but people realized that to work out the complexity of stellar evolution required computers and these massive programs. All right, so this is something that we can work on, with computers nowadays. Is let's say you have a young cluster of stars that is formed. So we see stellar clusters. Probably the easiest one or most obvious one to think about, is also happens to be in the constellation Taurus. It's called the Pleiades, also known as the Seven Sisters. So this is a stellar cluster, a cluster of stars that where all the stars are approximately the same age. And what happens with these younger stars is the more massive stars will fall down onto the main sequence first, and then as you get to smaller and smaller stars, or less massive stars, they will fall onto the main sequence in a much later. Okay, so we see examples of this, and of course our theories predict this. And then, but what about the other, the other direction for stars that are star clusters that are much older? So remember, a cluster, you have lots of stars that were born about the same time. All right, so from the same stellar nursery, if you will. So with those stars, what we find with our computer models, and of course when we look in reality as well, out into the night sky with telescopes and actual measurements, is that we find for those clusters. So let me back up just a little bit. So we think, of course, that the more massive stars, the more luminous stars, will leave the main sequence first, and then they will, in a particular cluster, the more massive stars leave first, and then as time goes by, the more and more of the stars within that cluster will leave the main sequence, and they'll do it in the order of from greatest mass to least mass, right? And where they have left the main sequence is called the turn-off point, and we can actually measure that. Okay, so here's an example of there's the stars collapsing. Still some younger stars collapsing, falling onto the main sequence, and then as time goes on, we see situations where the star cluster, older star clusters, you're going to find more stars have left the main sequence. Younger star clusters, only just a few stars, the really massive stars have left the main sequence. And then, of course, very old stars, very old star clusters. Okay, so we're talking about clusters of stars, groups of stars that were about the exact same age. Those stars, their turn-off point is much further down the main sequence. All right, so that's it for chapter 12. We'll take up chapter 15 in the next video.